So I want to acknowledge, first of all, my collaborators in this project, Michelangelo Naim, Antonis Georgiou, and Misha Katkov, were all at the Weizmann Institute. Michelangelo now just moved to MIT. And Sandro Romani was involved at the beginning stages of this project, and he's now at Geneva. Okay, so the idea that, okay, not everything is seen, sorry, you don't see a picture here, but I just, this was just an introductory picture illustrating that memory is quite a complex, human memory is a very complex phenomena. It has different stages, acquisition, maintenance, recall. All of these stages are quite unpredictable and I would say fragile. Sometimes they don't really work very well. So studying this mathematically sounds like not a very obvious thing. And indeed, it's quite a complex thing to do. And even quantifying memory is not such an obvious thing, because if I give you, let's say, something interesting to remember, some like a lecture or a story, and then you will recall it back to me, it's not easy to put the numbers into this recall. And psychologists developed some paradigms, experimental paradigms that go around this problem. And in particular, the paradigm that I will describe here is studying memory for random lists of items. So in particular, for example, you can just put randomly words in a list. So there is no information that this list will contain. And this is, of course, a big drawback, because this is not the real thing that we usually remember in life. But on the other hand, it makes experiments very precise. And so this is like a usual trade-off between these two things. So I will discuss two experimental paradigms with the random list of items. One is the recall. So that will be the main part of my presentation, where subjects are asked to recall as many items from the list as they can in any order. And then we can, of course, just count how many items people can recall. So this will be an easy quantification for this task. Or alternatively, I can present one of the items from the list and against the destructor and ask the subjects to identify which one of these items, of these presented items, was in the list. So this is called the recognition paradigm, because what I'm testing here is whether the subject can recognize which item was in the list and which was not in the list. And this is, again, can be easily quantified, because I can just count how often people give a correct answers to this paradigm. Okay, so these experiments were really done numerous times over the course of more than 100 years. And I would say the peak of these experiments was quite a long time ago, also about 50s or 60s of the last century. Then it kind of decayed, even though even now there are some group of researchers who still performing these experiments. So there is a great number of results that were obtained, and I, of course, cannot give you any serious review of these results, so I will mostly present our own work. So at some point we started doing our own experiments using the modern technology. Now you don't, so I don't have my own lab, but these experiments can now be done over the internet using the Amazon Mechanical Turk platform. So this allowed us to do our own experiments, which were better tuned to our models. So I actually decided that in this presentation, I will first present you some of the experimental results, and then we'll switch to theory. I'm just trying to so we use this paradigm of random lists of items. We either use we vary the length of the lists. So we had a list of randomly assembled words taken out of the pool of roughly 800 common nouns. We had a list of different lengths, from very short ones, like 8 words at the list, to the long ones, 512 words. We experimented with different presentation speeds. So I will show you the results for 2 presentation speeds, either 1 second per word or 1.5 seconds per word. We also used other items. In particular, what I will present you here is the short sentences, which express some common facts, something like Earth is round, birds fly, etc. So we assembled a pool of roughly 300 common words. We have 4 different lists, length links for this common fact, from 8 to 64. The presentation speed was a bit slower because it takes longer for people to read the sentences. And we try to do the experiments in a very precise and careful manner. So we have people divided into groups, and each subject was performing one recall experiment, so just for one condition, under one condition, and one recognition trial under the same condition. So, for example, if you have a certain subject that made the recall experiment with, let's say, 64 words presented at 1 word per second, so on the other day he would perform one recognition experiment of another random list of 64 words presented with the same speed, and he would only answer one recognition question. So the reason we did it this way is that there are a lot of effects that we wanted to avoid. So, for example, when people would repeatedly do recall experiments, they slowly become better by developing certain strategies that we didn't want to deal with, because this obviously complicates the analysis. And also, when they do multiple recognition questions, there are some interference effects. So the recognition performance slowly degrades. So that's why we limited these experiments to just one recognition question. So these experiments, as I said, many people did these experiments before us, so there is nothing really new here, except for this fact that we have many subjects using these technological advantages that we have now. And we did many different conditions, and we controlled very precisely the experimental conditions. And also we had the people doing this recall and recognition experiments. The same subject did both experiments. So let me show you some of the results that we obtained in this experiment. Okay, so this is a summary of our recall experiments. So what you see here is the average performance of subjects that are divided into all these experimental conditions. So we plot the average number of words that were recalled by all the subjects that performed experiments with a particular list length. L here stands for the number of items in the list, from 8 to 512. And there are 3 conditions here. So either list of words presented with a low speed, slow speed, faster speed, and a list of short sentences. And you see the tendency here is that people recall more items when the list becomes longer, and there is no limit here, so they can recall as many as several tens of items. Sorry. They recall more items when the presentation speed is slower, so that's kind of an obvious fact. And but you see that this is especially pronounced when the lists become longer. So for relatively short lists, there is not much difference, not much effect of the presentation speed. And also, there is quite a universal behavior until this for the short list. So it doesn't really matter if we have sentences or words. The recall performance is pretty much the same. Okay, so all of this, not all of the facts, but many of these observations were done before. So in particular, this type of dependency on the recall of the length list, on the presentation speed is not something that we discovered. So we are just confirming here a previous observation. This universality is, I think, is quite new. I'm not aware of other studies where this universality was observed. And these are results for the recognition experiment. So here we have the experimental measure that I'm showing you is the percentage of correct answers, C. So how often, what is the fraction of the subject that responded correctly to this recognition question? So the tendency here, that the main trend here is that for longer lists, the recognition becomes worse and gradually declines towards the random guessing, which would be 50% correct response. And again, a slower presentation speed results in better recognition. So you have a more percentage, more correct answers than for higher presentations. And this becomes more and more pronounced when the lists become longer and longer. And for shorter lists, there is not much difference between all the conditions. Okay, so this is again not for the most part, these are very well-known effects. Now I will present you a new observation, which is that there is something universal, some invariant about all of these results. So if you introduce this measure, this new variable, which I call x here, which is defined via this result, these measures that I just introduced. So C here stands for percentage of correct answers in the recognition experiments. R stands for the average number of words recalled during the recall experiments, and L stands for the total number of items in the list. So if you combine the results of recall and recognition experiments for identical condition, then the value of this memory invariant is, you can guess from the name that I give it, is more or less the same no matter what experimental conditions we apply, right? So this is the same results replotted in terms of this new measure X. And you see that pretty much no matter what experimental conditions we apply, the value for this invariant measure is more or less the same. Okay, it's not identical, of course, and there is some transient changes, but it slowly converges to some asymptotic values when the L grows. Okay, so this is my main observation that I wanted to present to you. And now basically the rest of my this part of my lecture will be presenting the theoretical framework that explains how this invariant comes about. Obviously, we didn't just guess that this invariant came out of the model that we developed, but for this talk, I decided to present it first before to use the model.
Could I ask a question?
Yes, sure.
So is there an intuition of why x should scale like the square root of L?
What is the, let me just tell you what's the, let me just illustrate you some of the points here, just to give you this idea that even though the invariant stays the same, but the individual parameters that go into it are actually quite different. So for example, these are the results for, I don't know if you can see my pointer, but if you see the pointer, what I'm showing you that, for example, for the list of the 512 words, for slow presentation speed, which is the blue curve, you have 75% of correct answers, and you have on average 35 words that people can recall. This goes down to 20 words when the presentation speed is faster, and correspondingly also the recognition performance becomes much worse. But if you go to the other end of this curve, you see here that the recognition is much better, and but the recall performance is much worse. Obviously, out of 8 words, you can only recall, in this case, on average, people can only recall about 5 words. But if you compute the invariant, it's more or less the same. And I just want to give you a preview of the theory. So what's this? What is my model that I'm going to present you soon? What does it predict? It predicts this particular value for the invariant. So it's trying to get rid of this. Okay. So the model that I'm going to present to you predicts that the value for this invariant should be about 0.46, which is the square root of 2/3 pi. And you see this is quite close to the data for all conditions, and especially for longer lists, it's becoming closer and closer to the experimental data. It's not so close for the shorter lists. Okay, let me now present you the derivation of this result. So it is based on several assumptions. So I want to introduce you now these assumptions one by one. So first assumption, which is actually a crucial one, is that I'm assuming that after the presentation, the certain number of items remain in memory, and some of them are forgotten, right? So there is some kind of binary process, the discrete process, whereas some of the items are not in memory anymore, are completely forgotten. And if this is the case, so we can estimate the number of items that are in memory based on the results of the recognition experiment according to this simple formula. This simply assumes that if you remember the item, then you will always give a correct answer to the recognition question. And if this item is not in memory anymore, you will give you a completely random answer. And so by assuming this dichotomy between remembered and non-remembered answer, you can relate the number of items in memory, which I call here M, according to this simple formula. So let's say if you have a completely random answers with 50% probability of the correct answer, you get 0. You get 0 here, and if you have 100% correct answers, you get M equal. Okay, this sounds like an innocent assumption, but this is by no means the correct thing, right? We have no way to know if this is true or to what degree is true. And many people actually have a very strong criticism of our work based on this assumption, because the alternative way to see this is to say that items from that all of the things all of the items in the list remain in memory to a certain degree, but different items have different degree of familiarity signal associated with them, and so recognition is more or less like described by the something like signal detection theory. So more familiar items are recognized with a higher probability than less familiar. So this would be an alternative view, but the theory that I want to present to you assumes this dichotomy between remembered and forgotten items. Okay, so given that the certain number of items remain in memory, so now we're assuming that only these items can be recalled, and obviously the other ones that are forgotten can never be recalled. So then, so how is the recall process occurs? So I assume there are two more assumptions about the actual recall process. So one assumption is, should be very familiar to people who do neural networks. So I simply assume that every memory item is encoded as a sparse random group of neurons. And it's very important for the theory that I want to develop for you is that it's both sparse and random. So the random means that the neurons that are encoding each item are picked up randomly from the network. And the sparseness means that only a small fraction of neurons in the network are encoding each item. And finally, there is a third assumption, which is the crucial one for developing the calculation, is that the recall algorithm, the actual recall algorithm, is controlled by the overlaps between these random representations. So if we calculate the number of common neurons that encode two particular items, mu and nu, the recall algorithm that we hypothesize works like the following. So we assume that the first item is recalled by chance, and then the process search for the second item, which has the largest overlap with the first one. So this is illustrated here with these blue circles. And then the recall transition happens to the item with the largest overlap. And there is just one exception to this rule, is that you cannot go immediately back and recall the item that was recalled just before that. So for the second transition, you have to find the item that has a largest overlap, except for the one that was just recalled before. So this transition that is now shown in the red arrow is forbidden. So the actual transition will happen to the next item. So in this particular situation where you have 4 items in memory, the process will just cycle over these 3 items. In this example, 3 items out of 4 will be recalled, and the last item will never be recalled. Okay, so these are the assumptions that I'm making. So now the problem becomes mathematically well defined, and now we can address the main question that we want to address: is how many items will be recalled in the list of a particular length. So this is another visualization of this algorithm. So if you have m items in memory, so we have a matrix of similarities, which are the matrix of overlaps that I showed you in the previous slide. And what we have to know, according to the assumptions, is only the position of the largest element in each row and the second largest element. So I put here a black spot at the position of the largest element, and red spot at the position of the second largest. And on the right, you see the graph where the same process is illustrated. And the algorithm that I described works like this. So let's say if you start the recall from the item number 1, you have to find the position of the black spot in the first row and put the error to the in this case to the 14th element. Then you have to look at the 14th row and find the largest element in the 14th row. This would bring you back to item 1, but because this is forbidden by the algorithm, so you have to find the red spot here. And so the next transition will be to the item number 10. The same thing from item number 10, you go to 7. And so every time the transition happens to the second largest element in the similarity matrix, I put a red arrow. And every time it goes to the largest element, I put the black arrow. So it's easy to realize that if you plot these trajectories, on average, half of the arrows will be black and half of the arrows will be red. So what can happen is that I can subsequently visit the new items, and at some point I will invariably collide with an item that was already visited before. So in this example trajectory, this happens at this moment when I come back to the element number 10. So on the first account, the next transition was from 10 to 7. But when I come back to element 10, because the previous transition was along the red arrow, now I can also choose the best transition. So the transition from the 10th element to the largest, from the 10th to the largest overlap, which in this case is going back in the opposite direction to the item number 14. Then from item number 14, I go back to the item number 1. And then I continue my trajectory. I recall a new item 13 that was not recalled at the beginning. So this opens up a new set of items that I can now recall until finally I converge to the cycle. So the convergence to the cycle happens when I repeat the same transition for the second time. So the moment I repeat transition from item number 12 to item number 16 for the second time, because this algorithm is a deterministic one, the future trajectory will repeat the same route, and I will converge to a cycle. So after this converges to a cycle, no new items can ever be recalled. Okay, so in this particular example, this is the trajectory. Of course, if I have another similarity matrix, the trajectory may be completely different. So the number of items that can be recalled is a stochastic variable, and what we want to analyze is actually the average length of this trajectory. So this is a very complicated, mathematically, it's quite a complicated model because of this complexities of the recall trajectories and this dependency of the rule on the history of the recall. So there is no, or at least I don't have a complete analytic solution to this problem. However, in the limit where these encodings are very sparse, so when the in this limit you can neglect the correlations between the different elements in this similarity matrix. And in this case, there is a certain mathematical trick that allowed us to calculate the average length of the recall trajectory. So the model in its complexity is still not solvable. So, but there is some kind of a miraculous trick that allowed us to calculate the average trajectory length in the asymptotic limit where m becomes large. So let me show you the result. And I decided not to give any mathematical details here because it would really take too much time and will not let me show you all the results. So we have this recent publication where we published this derivation, but here I'm just telling you that that asymptotically for large values of m, the average length of this recall trajectory is given by this formula. So it's proportional to square root of m. But again, to answer, so at this stage, maybe I can give you some intuition, because the square root of m is the result of this randomness, this assumed randomness of this similarity matrix. So basically, this is kind of a random walk over this similarity matrix. So this is the responsible for the square root dependency of this result, and the coefficient is has to be calculated mathematically. So this is the asymptotic result. Okay, and this is what gives rise to this invariant, right? This is some numerical simulation that show that in fact if the similarity matrix, if the encoding becomes sparser and sparser, the behavior converges to this asymptotic behavior, and in fact it's actually a very good approximations even for relatively small values of m. So this it's for all the relevant values of m that we have in our experiments, this is a very good approximation to the true behavior in the sparse limit. So that's how we came up with this invariant, because if you now replace m by its calculation through the performance in the recognition experiment, so that's how we get this invariant x. And from the equation above, we can see that the theoretical prediction for the value for this invariant is square root of 2 over 3 pi, or approximately 0.46. This is if you present the results in a more kind of intuitive way, where we plot the average number of items recalled versus the number of items in memory as estimated from recognition experiments. That you see how close the results are to this experimental, this theoretical prediction with all possible conditions that we tried. Right? So overall, we have quite a good precision with which the experimental data lies on the theoretical curve. Okay, so all these results were presented in this publication. I want to show you some new developments that we recently did. And this was mostly the motivation for going beyond these results was actually in response to a lot of criticism that we got when presenting this work, especially to psychologists, is that that concerned this first assumption, right? Because many people were very unhappy that we made this assumption that some of the items are in memory and some of them are not. And in order to somehow generalize our theory, and we decided to go beyond the average. So, and in fact, you can from the mathematical derivation for this model, you can actually go beyond the average and write down the expression for the distribution of recall performances. So for a given value of m, you can write the asymptotic distribution of r, and this has this simple form. And from this simple form, you can derive all the moments, not just the first one. So the first moment, which is the average, is given by this equation that I presented to you in the earlier slides. But you can look at the second moment, which is given then by this simple formula. So the second moment, or the average square of R, can be calculated as 6 times M. And this, if you now look at this moment simultaneously, you can actually eliminate M and relate these two moments to each other. And this results in this very simple relation that doesn't really depend on M. So you can go and test this without doing the recognition experiments. Right? So this is the advantage of this analysis. Unfortunately, there is some caveat here. So this the caveat is that these calculations were performed for a fixed value of M. And we know that in our situation, M cannot be fixed because we have a group of people performing this recognition experiment, and it's highly unlikely that every subject will remember exactly the same number of words. So there is another contribution to the distribution, which is the differences between the subjects in terms of the individual values of M. And we have no way experimentally to evaluate this. So there looks like this is really a dead end. But we found a way to make some still contribution from this analysis. So this is basically what the true values for the moments are. So if we would know the distribution of M over the subjects, then we could calculate the first and second moment by averaging over this distribution. Now we don't know the distribution, so the best we can do is we can put the bounds for the second moment if we for the constraint of the first moment. So if we measure the average number of words recalled, we can put some lower and upper bounds on how on the second moment of R. And this is the lower bound is given by the equation that I gave you before. This is achieved when P of M is just a delta function. And the upper bound, you can prove that it's achieved when P of M is the sum of two delta functions, one corresponding to no memory at all. So if some of the subjects don't remember any words, and some of the subjects remember all of the words, we have a sum of two delta functions, then you can calculate what's the value for the second moment will be. And so this will be the upper limit. So the model is only compatible, will only be compatible with the data if the second moment for our data will be between these two limits. And so we can see now, we can analyze our data and see where the real experimental data is in terms of this thing. So this is a analysis of our experimental results. Again, we divide them into seven different values for L, and for every L we have different points here corresponding to words presented with two presentation speeds and these sentences for facts. So you see that all of the data, the red curve is the lower bound, which is the same for all of these graphs, and the blue curves, blue straight lines are the upper bounds. So all of our data are in the correct regime. So it means that the model is compatible with the data. And in fact, they're quite close to the lower bound, but they're actually all above the lower bound. So you can go further. You can not just to make sure that the data lies in the correct regime, but you can also use these two the values for the two moments and try to infer the distribution of M. So we have, as I said, we have no way to measure experimentally what the distribution of M is, because every subject only answers one recognition question. So we only know for each subject whether he answered correctly or not correctly to this recognition question. But given these two moments, we can find the distribution that is we can optimize. We can choose the distributions that results in the closest possible values for the first and second moment to this experimental data. And this results in this, I show you, so we did it for all our experimental conditions. I'll show you just a few examples. So this is an example where you have a list of 32 words presented with a slow speed. So this is the experimental recognition, the distribution of the recall performance. This is the inferred distribution of number of words remembered. So you see that the model predicts this wide distribution of M's. So some people here don't remember anything. Some people remember all of the words. And there is this wide distribution. And this is the predicted distribution of recall performances that you can now compare with the actual one that we measure experimentally. So this is another data point where 32 words are presented with faster presentation, and this is the same 32, L equal 32, but instead of words we have a facts presentation. So so we did this. We repeated this procedure for all our experimental conditions, and in all conditions but one, the predicted distribution of performance was statistically indistinguishable from experimental one. So this means that our model not only predicts well the average performance, but given this procedure, it also predicts well the full distribution of the recall performance. We can go back and then we can also make a prediction of the fraction of the average number of remembered items using this inferred distribution and compare them with the ones that we measured in the recognition experiments. And as you see here, we have a very good match between predicted and measured recognition number of items in memory after the acquisition. Okay, so these are all the results that I wanted to present regarding the recall experiments. I will take a few more minutes to present another models that we developed for memorizing items. So can we really predict theoretically how many items people have in memory after the acquisition, after presentation? And this is again very popular topic in psychology. So basically it relates to the forgetting. So how forgetting mechanism works. And in psychology, people were discussing a lot this issue, and they came up with a measure that is called the forgetting curves or retention curves, which basically measures what's the probability to retain an item in memory for different amount of time that is lapsed between from the acquisition. And many of the experimental results were fit by this mathematical curves. Generally, the best fits were obtained when people used the power law forgetting curves, which is a very interesting observation, because it basically means that some memories can remain in memory for a very long time. So we asked ourselves, can we actually come up with some models that would allow us to theoretically predict the form of these retention curves? And again, the question is how universal these retention curves are. That's another very interesting question that we wanted to address. Let me skip some of the technicalities here. So we just came up with an idea. So this is really has no experimental motivation. The model that we came up with is like a game model. So let me show you how this works. So let's assume that every item that we have in the list, so let's say every word has a certain degree of importance, which is could be just captured as one number. Let's say this is a simplest version of this model. And let's assume that every time a new word is presented, all the previous ones that are still in memory and have a smaller importance measure are erased from memory. So this is called a retrograde interference mechanism. Okay, so this is illustrated in this cartoon. So you have, let's say, 4 items in memory, 4 words in memory. You present a new one, and this new one erases these 3 words because they have a smaller importance measure, and then you are now left with 2 items in memory. Okay, so now it's very easy to calculate what's the probability that a certain memory survives t time steps, because the memory can survive for t time steps only if all the memories that are presented in these t time steps have a smaller importance measure. And if you assume that this is a completely random process, then the chance that this memory survives for time t will be simply given by 1 over t plus 1, because this is the probability that out of t plus 1 random numbers, the first one is the largest. So this has a power law relation, so this is a good feature. However, there is a serious problem with this model, because if you now estimate how many items remain in memory after t steps of this process, we have a very unsatisfactory results, because this means that the number of items in memory grows very, very slow, which cannot be a realistic number. So to generalize this, to solve this issue and to generalize the model, we assume that the importance is not a one-dimensional feature, but rather you have several dimensions of importance, which could correspond, for example, to different context, the importance in different contexts, let's say social context, survival context, etc. So this illustrates this idea if you have 2-dimensional importance measures. So every memory can be specified by 2 numbers. And then you only erase the memories that were acquired before due to the presentation of the new one, if the old memories have a less smaller importance measure in all of the dimensions. Right, so this makes this process mathematically very interesting, because now you can have pairs of memories that cannot be compared to each other, right? So, for example, this 2 memories, let's say blue and red, cannot be compared, because according to one dimension, the blue memory has a larger importance, but according to the other dimension, this is reversed, right? So this set of memories becomes cannot be strictly ordered, and it becomes an interesting mathematical problem, again, which is we don't know how to solve it completely, but there is some mathematical trick that allowed us to write down this recursive equation for the retention curve. So for every n, you can express the retention function of this model through the retention curve function of a model with n minus 1. And because we have an analytical solution for n equal 1, so you can then use this recursive equation to calculate the retention curve for an arbitrary n. And this is just an example. This is a graph shows how the retention curve looks for different values for different dimensions n. And we tested this model with a recognition experiment where we present a long list of words. And from time to time, we do the recognition experiment, recognition test. This is a list of words. And we do a recognition test for the word that appears either 2 words back, or 10 words back, or many words back. And we use this 2 words back recognition just to select people who are paying attention to the task. So because this should be a very easy question. So we only consider subjects that do perfect recognition for 2 back. Okay, so this is the result. This is the plot with the results of this recognition experiment. So this is the 2 back task for taken at different times over the presentation, and you see that we only selected people which have a perfect performance here. This is the performance of the 2 back recognition test. You see this is not perfect anymore, but it doesn't. There is no decay of this performance. No matter when we ask this recognition question, the performance is more or less the same. So this confirms our assumption that that there is no proactive interference. The memories, the words that are presented at a given time don't erase the memory of these words, don't erase the words that are presented later. And this is the main curve that I want you to focus on. So this is the recognition performance about the word that was presented at the beginning of the list as a function of the lag between the presentation and the test. Okay, so you see that there is a decline of the performance towards the 0.5, which is the chance performance. And these are the theoretical curves that correspond to different values of n. And this shows that the experimental results are best explained by the model where we have a 5th dimensional measure for the importance of the memories. Okay, so this is, of course, doesn't mean that the model is correct. It just means that the mathematical form of the retention curve for the 5th dimensional version of this model fits quite well the experimental data where we have a list of common words. And finally, I want to present you some new results where we ask the question how universal this observation is. So whether this 5th dimensional version of the model would work well for different experimental conditions, and most importantly, for different types of memory items that we can try. So to test this, we repeated our experiment where we replaced the words with these simple sketches. So let's say instead of presenting the word hammer, we can just show a sketch of a hammer, or the same for a basket. Or we can show the sentences that kind of define the certain word. So for example, we can say that coal is used as a fuel. So this is a definition of the word coal, or a coffee is grounded from beans, etc. And so these are some still ongoing work. So this is but the very interesting observation that emerged is that there is actually no universality. So as opposed to the recall process, the recognition results were not universal. And somewhat surprisingly, we had a better recognition performance for sketches and sentences that we have for individual words. And this better performance was explained quite well by the 7-dimensional version of our model. This, of course, has to be tested with more data. So you can then, the interesting question then is whether indeed, no matter which the question becomes now for the future study that we are trying to pursue now is whether different types of memory items will be explained by our model for different values of this dimensionality, and whether you can somehow predict this dimensionality for some principles. So all of these are just the questions for future studies. Okay, I think I should stop here, and I will be happy to answer questions if you have some. Thank you for your attention.